Hi, everybody. So today I'm going to talk about microservices, which is a painfully trendy topic right now, and also Go. So has anyone used Go here before as a programming language? Okay, so a couple of people. Great. So don't worry, there's nothing like too Go specific, but just like a little bit how Go is great, how you should definitely use it, that kind of thing. Okay, so first off, I'm Matt. So my Twitter handle's here. If you want to ask me any questions, we've got Q&A after this talk. And I work for a startup called Mondo. So Mondo are a startup based in London. We're building a new bank. And that's an interesting thing in the UK. Like there aren't many banks. There's 5 really large banks. They control about 90% of the market. And the problem is for customers, like banks haven't really changed. This is kind of how I see banks. They're extremely old. They've been around for hundreds of years and they haven't evolved with the times. They are stuck in kind of an age where computing is kind of large monolithic mainframes. Now this is real. This is an IBM System 360. They're amazing. You could buy them in the 60s. And cool fact, if you wrote code on one of these, you can still buy servers that will run that code. So you don't need to change it. It's great. Like you can just write some code, retire, problem solved. And the problem is that this has happened. So we still have large banking systems that are written in COBOL. And developers who write COBOL have largely retired, which is a problem if you want to maintain these software systems. It's great if you're a COBOL developer, because you can get paid an infinite amount of money. I wish I'd learned COBOL. It would have been amazing. Anyway, this is not really how 2016 is. So in the modern world, we expect everything to be on our smartphone. And I expect to be able to do everything and control my money with a few taps on my phone. And that's really what that's mobile first. And we can do that because we're writing all of our technology from scratch, which is usually quite a risky thing to do. So basically, we're mobile first. You can do normal things like get your bank statement on your phone, except we provide contextual information. You can see like the Twitter logos of the places, very useful, very useful. But also like where you purchase things. And we can break that down into spending categorization and give you advice on how you can save money. We can also do contextual searching. So you can search for an emoji coffee cup and we will find places that sold coffee that you shopped at. But you can do things like this month, you are traveling with business, you can take pictures of receipts, apply that to your normal bank statement. And this is a really easy one. So who has lost their debit card? Like ever? No one. No one's ever lost their debit card. You're all very responsible people. Okay, so I've lost my debit card loads. So in the UK, when you lose your debit card, you have to ring your bank, which takes 30 or 40 minutes. You get a replacement, and that takes 5 to 7 days. So what if, hypothetically, you could turn your card off and it no longer works, and then you could turn it back on again? Mind blown. This is obviously a flag in our database. And that's the kind of things, this is a feature that banks should have provided to customers 5 or 10 years ago. I mean, we wrote this in like 2 days. Like it took no time at all. So that's kind of the background. But if you're building an application from the beginning, where would you start? You have to make a lot of technology decisions upfront usually. And that's not what you want to do as a startup. You want to build a product, you want to test the product with customers, and you want to see if you actually get any traction. And then you hit your scaling problems. Like, that's fine. But like, if you do, then hopefully you have enough money, you can employ more developers, and you can fix those problems. So in our case, we'd usually start with a simple application and a database. And this could be in any language. A good example would be Rails, maybe. So if you're a Ruby shop, if everyone knows Ruby, you can build a demo application, you can build something basic that you can test with customers extremely quickly in a matter of weeks. And then over time, you're going to add more and more features to this. So your application is going to get a lot bigger. I don't know if anyone's worked on large Rails apps. I'm not picking on Rails specifically here, but anyone who's worked on large applications knows how like things slow down and it's harder to get features in, it's harder to make changes. And they just get more complex. And you then end up adding kind of like things like additional databases to do different kind of types of work, things like search, things like caching, and various other things that you kind of end up being very important to your kind of product. And the end result is something that's extremely complicated. And in our case, it's this huge monolith. So we end up with one large application that we deploy repeatedly. And anyone who wants to make a change in our entire company has to somehow get a change into our code base and then do a deployment to all of our production systems. And that requires a lot of coordination and it slows us down as a company. And it also makes me very unhappy, like this guy. So what we want to do really is, as a startup, we need to move very, very quickly. Like there are companies in our industry that spend £3 billion a year on IT infrastructure. Now, if we were a startup and someone gave us £3 billion, that'd be incredible. But they don't. And these are very large companies and they know that they need to change. So we have to be faster than them. We have to like provide features far more quickly than they can until they slowly evolve their business model and catch up with us. So we have to be faster. So what we want to do is take our application and break small chunks apart, and we end up with a large number of different applications. And this is kind of all people mean by like microservices. We have a number of applications that communicate with each other, and as a whole, they provide our product. So why would we start with this from scratch, the Mondo? And this is specifically it. We need like velocity, we need speed, and that is our product. We have to ship code extremely quickly. And as a result, we need to do everything we can as a team to make developers more productive. So we end up with a large number of small applications, and they have a few kind of key things that we're looking for. So one is something a lot of people talk about, which is single responsibility principle. So by this, I mean, every application that we build, we end up with, it does one job and it does it extremely well, and it's very focused. And that means that we can pick the appropriate technology. So we might do that in a different programming language. We might use a different framework. We might use a different database. But fundamentally, there is a service that has some form of maybe HTTP API or some way of communicating with it. And we would have this one application. That means we can just focus on that one thing. It also means if you're working as a large development team, then one group of developers can work on that application and others can work on different applications, and they don't have to talk to each other. So your development speed is faster. We need to use what we call a bounded context. So we're going to take all of banking, which is quite a large problem, and we're going to break that up into small areas of like business functionality. And then from that, we can build our software that solves that problem. And then on top of that, once we've built these applications, we end up with quite well-defined interfaces. So we have very specific contracts that our applications have. And as a result, we can then build further applications on top of that. So we can compose like more complex applications out of these smaller building blocks that are very well established. You don't need to because there's an API that is being very well defined. So how do you get started? And this API is actually available to third parties to build applications on top of. And when they make requests to our infrastructure, they're going to hit a load balancer right at the top. And then behind that, we have some form of HTTP API. So we provide HTTP with JSON as our kind of encoding. And that's actually like a routing layer that will route traffic into our infrastructure off to the correct application. And it'll do that through some form of transport. This could be HTTP, it could be RabbitMQ or AMQP, some kind of messaging bus. And then behind that, we'll have a number of services and a database behind them. And crucially, each one of these services has its own database. There's no like kind of cross access between different applications, because if we change the data format in the database, we'd have to communicate with the team, all of the teams who are writing or reading from that database. And that would again slow us down. We wouldn't have this well-defined interface at the top. So behind this, one advantage of this kind of pattern is right at the top where we have our HTTP API is what we call an API gateway. So it's a kind of common design pattern. And the advantage of this is if you're not starting from scratch, if you're migrating, you can actually slot this in as a proxy at the top. So you might have your current application, which could be written in any technology at all. And then you can slot in kind of a gateway at the top, which is just a reverse proxy. And then behind that, that will proxy your traffic to the application, which you can move to one side and slowly intercept traffic and kind of break your application apart. And the startup I worked at before at Halo, this is exactly what we did to move all of our kind of production traffic over from an existing like PHP, a series of services that were written in Go, which brings me on to Go. So only a couple of people have used it. Has anyone heard of Go? Hands up. Okay, slightly more. Cool. So Go is a relatively new programming language. It's been around for about 6 years now. And it's got quite a few things that make it really, really nice to work with as a team. The language itself is very simple. It's also statically typed. So we get rid of like a large class of errors where you maybe convert between different types. As a bank, it's obviously quite useful to not accidentally convert floating point numbers to integers. So statically typed languages are great. And you can also do lots of other things like static analysis. So you can run tools in your continuous integration pipeline, which will check for particular classes of bugs. On top of that, Go itself is statically linked. So when you compile it, you end up with a single binary that has no runtime dependencies on your servers. So unlike most other frameworks where you'd have to, like, if you're using PHP, I was a PHP programmer for ages, I would have to install PHP on the servers to then run my code. If I'm running Java, I have to run my Java code within a Java virtual machine, and that has to be installed on the machine. In the case of Go, it has no dependencies at runtime at all. And in fact, if you statically link it, it has no C runtime dependencies at all, which means you can take a binary, as long as it's the right architecture, say a 64-bit, and you can put that on S3, and then you can copy that onto a server, and you can run it. And you don't need to do any preparation. There's no installation. And that means you can run like really simple operating systems. You can get a far closer to like immutable infrastructure that a lot of people get to, because you don't have to use an image and then run lots of packages, and then you can run your code. Also means deployment is super easy. You copy a file and you execute it, and that's literally it. On top of that, the language itself has an extremely comprehensive standard library. So the language itself is very simple, but then the standard library that comes with it has pretty much anything you need it to do. So as an example, networking, you can run a HTTP server with about 4 lines of code. And as of Go 1.6, if you'd run it on Go 1.5, you'd have a HTTP1 HTTP server. And if you then recompiled it with with Go 1.6 point something, you'd end up with the same code that would just magically upgrade to HTTP2. And that's because like the contract that the Go developers have is that your code will always be backwards compatible, but they can transparently add these features in. The other thing that Go is amazing with is concurrency. So has anyone like used languages that are like very heavily threaded? So like Java, you have to like fire off new threads. You have to declare a new like thread class or something. If you've ever used threads in Ruby, like you probably are screaming somewhere. In Go, you get things called Go routines. So you can have any function and you can write the word Go and a space before it, and it will now execute concurrently. And that's amazing. It's obviously kind of dangerous sometimes, but it means that you can write this like extremely flexible code that can be very asynchronous. And the cost is extremely low. Like some of the production systems at Google that use Go routines quite heavily will be running hundreds of thousands, if not millions of Go routines. And that's just not something you can do with like a normal threaded model. And Go just deals with all of that for you. On top of that, it has really good interface support. So interfaces are quite simple in Go, but it means that if you have an object that has a number of functions, another object that has a number of functions, you might have an interface that has a subset of those, and actually both of these objects would still satisfy that interface. And what that means is you may have a transport that was HTTP, and actually all it needs to be able to do is kind of send and receive data. So you'd have an interface that did that, and you could actually potentially swap that for an implementation that used a different messaging transport, or including perhaps like an in-memory mocking system for testing, so your test could be like an order of magnitude faster. So if you wanted to get started, there's a few libraries that you can use. So these kind of frameworks that allow you to really quickly build like microservices in Go. And they range from kind of Micro and Go Kit, which kind of are very strongly opinionated and allow you like kind of show you what you should be doing, down to like gRPC, which is essentially a kind of protocol level way of building services and servers that communicate to each other. So going all the way back to the beginning, what we have at Mondo is our load balancer. We have a HTTP API. And then behind this, we have what we call an API service. So what we mean by this is we have like lots and lots of different services, and we have some of them which respond to API requests. And then they kind of do other things by calling other services within our infrastructure. So these particular services would take the JSON in and then decode the JSON request and decide what to do with it, and then pass that on to another set of services. So as an example, we have an API, documentation online, and we have webhooks. So has anyone used webhooks here? A few people, cool. So our API allows you to register a callback URL that we will execute every time, and we'll send data about the transaction. So that means if I take my debit card and I go and use it in a machine, and I've registered a webhook through our API, then my service will receive a HTTP request with the payload of that transaction. And the fun part about banking networks is that they're really slow. So usually you'd receive this HTTP request before the receipt prints out of the machine, which is pretty cool. Turns out it's really easy to send HTTP requests in like 200 milliseconds. So all we're doing here is we have a /webhooks path on our API, and that has things like post to create a webhook, get to like list them, and a delete verb to delete that webhook. And this then maps into our webhook API service, which understands like what the JSON request is and how it should deal with that. And then behind that, it will send off requests to other services that it needs. And these internally, we use protocol buffers. I don't know if anyone's used that. So we use that as our kind of transport. It means that we get like binary encoding, and it's a lot faster. So we'll take a request in, and then we will make 2 further requests off to like authorize that the request is actually valid, and then perhaps put this webhook into the database in a different service. And these will have databases behind them. And these services could call anything. They could do anything they want. So they might call an external provider. If this was registering a new phone number, we might validate the JSON in a phone API, for example, and then we'd authorize the request, and then we might send a verification text message via an external API. And we do all of that as part of this kind of fan out into multiple services. And the advantage of this is that we can keep each one of these services very small. So our API, all it really does is maintains an external API to our clients that understands JSON, and it can do the request and response marshalling. And then we have other services that know how to store a phone, how to send a text message, how to do various other things. So inside one of these services, we kind of split this up into a few different layers. So we have handlers. So we have an internal framework that allows you to write these very, very quickly. And that means that we give our developers an interface that's really, really simple. So a handler that is going to take a request in and send a response back literally has to satisfy this Go interface. So a little bit of code, but yeah. So we have a type that's a handler. So that's just the name that we've given it. And this is a thing that takes any function that takes a request and returns a response and an error. And this is a common pattern in Go. Go tends to have multiple response types, and you return an error if there was a problem. You don't have exceptions like you do in most other languages. And that means actually a lot of your code is kind of checking for errors, making sure that you've dealt with errors correctly. And that forces you to write like really good code. Well, it forces some people to write really good code. So we have a number of these handlers, and these will be things like a different endpoints in our API that we've registered. And then behind that, we'll have some logic, which can do anything it wants. And then we'll have a number of libraries behind that perhaps abstract things like databases. What I mean by this is if you want to write, we use Cassandra as our main database. If I'm writing some business logic, I shouldn't need to work out like what to do if like one, where to get IP addresses from for our Cassandra servers, how to deal with the fact that these change over time, how to deal with things retrying perhaps if it can't establish a connection. All of those things should kind of be taken care of by a well-written and well-tested framework. So we have libraries internally that do this, and they do things like automatically pick up configuration and configure my Cassandra client with the correct IP addresses, stuff like that. So as a result of kind of pushing a lot of these things into libraries that we all share as a part of this framework, we get loads and loads of free things. So for example, service discovery, which in an architecture where you have hundreds of moving parts, you need to know where they are in order to communicate with them. We need automatic configuration. We need a standardized way of doing that across all of our services. Things like monitoring and other things that increase our reliability, like circuit breaking, so we can deal with partial failures within our infrastructure. And that brings us on to deployment. So we briefly, during the panel earlier, talked about Docker. We do use Docker. But the interesting thing about Go is actually there's no massive need to. Docker gives you like a standardized way of deploying units of code. But as I mentioned, like Go doesn't have any runtime dependencies. So actually like a lot of the things you have with Docker containers are you take a container, you would install the Ruby runtime, and then you would put your code in there. But you don't need that with the Go binary because it's just one thing that you put in one place and execute it. The advantage to using Docker, though, is that it's standardized. So if we take our Go container, we can build it into a really small image. Because we have no runtime dependencies, we can just compile the binary for Linux architecture and put it in a scratch container. So like our binary will be, well, the binary and the container will be of 10 or 15 megabytes, which is like quite small. Unlike a lot of other containers you see, which are potentially hundreds of megabytes because they need like an entire operating system and runtime inside. And the reason we can do that is because it's statically compiled and statically linked. And once we have our Docker container, which we could put anywhere, you have to put it in a Docker registry, which is quite irritating. But Amazon and Azure and Google Compute Engine provide these as a service, which you can sign up for. And then we can deploy them onto any number of other platforms. So for example, Google has, they provide Kubernetes as a service, which is their Google Container Engine. You can use the EC2 Elastic Container Service on Amazon. Azure launched a container service, I think 2 weeks ago or a few weeks ago. And that's essentially, I think, like a kind of hosted Mesos platform. And Kubernetes itself, which is an open source project from Google. So we actually use Kubernetes, which is really cool. It's really complicated. I don't know if anyone else has used Kubernetes here. Yeah, cool, one person. Anyone use Mesos here? No, no one. Okay, so we use Mesos for a while, and that's quite complex. And Kubernetes, I'd say, seems a lot, the design is like a lot better, but it's still very clearly in development in certain areas. So it's a learning experience. You really have to like test these things out, and you have to gain production experience in order to be confident enough to run a bank on top of this stuff, which is terrifying. But the advantage we get of using something like this is that we have about 105, 110 services, and we run in an Amazon region across 3 availability zones. So we have essentially 3 data centers, and we are going to run 2 copies of every service within each availability zone. So we have redundancy within an availability zone. We also have redundancy across availability zones, but we also have more than 100 services. So we already have 600 and something moving parts, and I don't want to manage that. So these kind of tools will do that for you. If you don't want to manage it yourself, then using something like Google Container Engine or Amazon's container service or the Azure one will do that and just manage it as a service for you. If you want to run your own infrastructure, then you also have to do that, but it's complicated. So given we have so many moving parts, we need to make our service a lot more reliable. And one thing we do automatically is things like topology management. So I mentioned before, we might have an API that talks to a service. And what I'm really saying here is like, this API will have 6 copies of that, and the service will have 6 copies of that. And in theory, they can communicate between any one of those. And the problem we'll have is that we'll have failure on any system that is complex. We'll always have kind of network failure or complete failure or like failure to access the database. So we'll end up with some instances of these that don't work. And we need a way to kind of detect these and like kind of stop them and fire up new ones. So we need our services when they're making HTTP calls to be able to manage this. And you might use like internal load balancers. You might keep a registry of the locations of all of these services. And that's kind of where service discovery comes in. So you have this constantly updated record of things you can communicate with. The other thing you end up with is where things are still up and available, and perhaps they say that they're healthy to all of your monitoring systems, but for whatever reason, one of the instances is slower, or it has a much higher percentage of errors. So in this case, you need to use something like a circuit breaking algorithm, which will preferentially select the fastest possible instance. And there's a few options to this. Specifically in Go, you can use a thing called Go host pool, which has come out of Bitly. And you can do things like use an epsilon greedy algorithm to preferentially select the fastest one with the least errors. But if that one goes away, it'll pick the next one, and it'll kind of move your traffic between all of the available instances. So this kind of stuff needs to be built in kind of quite early so that it's in your infrastructure, and your infrastructure can deal with kind of transient failures and kind of things that break, because they break all the time. Cool. And the other thing to make our infrastructure a lot more reliable is we push a lot of things into being event driven. So we use like a kind of event sourcing architecture. Anyone use that kind of thing? Okay, so has everyone seen like Twitter have a fire hose, which is like all of the tweets, which obviously need a very large network connection to be able to receive that. And they have a small number of partners which receive this stream of everything that happens on Twitter. And we have this internally in our infrastructure. So we have an event stream of everything that's happened. And that'd be things like, I've used my card and there's a new transaction on my bank account. So in that case, we'd have an API call that comes in, we register a new transaction, and then in here, we would fire an event that says this transaction has occurred, something has happened. And any number of services can then subscribe to that. It's kind of like a pub sub kind of system. And that means that we can, again, without me changing service B, we can add more functionality. So our teams, again, don't need to communicate with each other. They can just add functionality. And that means we can, as a company, move much quickly because we can build software really, really quickly. And again, behind these are just normal services. So we may make further internal calls, and that ends up being really complicated. And no one really knows how any of our systems work, which is terrifying. So this is kind of the inevitable thing that will happen with any large system and a large team of developers. There will be no way that I or anyone else in the team is able to understand the entire system. And I think if you're building any large product, that's like it's very unrealistic to think that you'll be able to know how everything works in perfect detail. However, you do need tools to be able to work out why these things break, because they do. And in our case, we use a thing called context, and we propagate this through. So what I mean by this is, given a kind of request response graph, so we have our API at the top making a request, and then that makes a request to another service, and then we get a reply and another reply. So right at the top, we can generate a unique ID for this reference. So this is a type 4 random UID. Pick any number you want. And what that means is every request that our API receives, we generate a completely random number, and that ID is then passed all the way through our services. So right at the top on our API, we would store that number in the request, and then we'd pass it down the next layer and pass it down the next layer. And in Go, we can use a thing called a context. So if anyone who uses Java, you have things like thread local variables. I think you have them in Ruby as well. Go doesn't have those. So we end up having like a variable that can, well, an object that can store any number of variables, this all the way through. So a context has lots of cool things, but we're only interested in this thing that allows us to store a value with a key. And in Go, again, this interface thing means it can be any type. It could be a string, an integer, whatever. So in this case, we'd actually store, the key would be like request ID as a string, and then the value would be the massive string that you saw a second ago. So once we have this, we can pass that all the way down. And all I mean by here is we receive a request, we generate this ID. When we go to make a request to our next service, we have a client, and that will take that request and serialize it as like a header, send it to the next one, which will then unserialize it. And then at all of these contact points, we have this request ID. So we can then measure lots of different kind of timing data and like what data we sent between the services. And we can scoop all of that up and send it off to an aggregation system. So here we might be measuring the time between we sent and then received the reply. So we have the response time, but we also have, so we know actually we could calculate the network latency, but also we can see if there was a problem rather than on the server, which replied really, really quickly, it was actually a problem on the client because it took a really long time to receive the response. These things are quite complicated. So we end up with a massive block of JSON, which is completely unreadable. This is actually a really small chunk of this. This is like a 4 megabyte blob of JSON for this particular request. And the reason for that is that this was one where we used our card. So we can take that and we can take all of the contact points. We know every service that this request went through because we have a request ID, and we know, and we can scoop all of that up and turn it back into something that is intelligible and that we can actually understand what happened. And we end up with kind of like flow graph like this. So this is actually me using my card in a debit card. I can't remember what I bought. So what we have here is this first section is actually the synchronous part of our processing. So right at the top, we hit our API. So we received a request from the card network, from our card processor. So I tapped the card on the machine. We received an API call. And then we sent that into a card API, which did some processing. Then we're going to do things like look up the card number, check that it's a valid card. So there's one service that's responsible for that. We then store a transaction. So we have a record that the transaction has been actually processed. We also update the balance. That's not quite as it's shown here. And then that's it. That's all we do. So actually in my app, I had like a series of really nicely formatted things, and none of that happens in the time that it takes to receive a request and send it back to our card processor. But what we do is we publish this event that a transaction was created. So at this point, if I looked in my app, I have no record that that transaction has appeared. We actually don't show it at that point. We send a push notification when you use your card, but again, that hasn't been processed yet. What it does mean is that although there are lots of other things we do later, the smallest possible number of them are on the critical path. So if all the other things broke, my card would still work in an ATM, in a store. And that's like the important thing that we're optimizing for. So then beyond that, we actually go to this transaction enrichment service, which scoops up lots of data from different places and tries to like apply more metadata to the fact that I've used my card. We do things like looking up the merchant. So we look at the store location. We try and match it to like an actual location, say on Google Places or on Foursquare or on Yelp. We then insert it into the feed in the app, and then we send a push notification. And the end result is that I get a push notification on my phone. But crucially, there's a coffee cup emoji there. Now, if I've never shopped there, how would we know that this place is a coffee shop? Like, what we've done here is we've taken the data we have, a very small amount. We've gone up and looked at like external databases. We've matched the fact that it is a coffee shop. And as a result, we can then send me a coffee cup emoji, which people love. This is how you delight the customer with emojis. You think I'm joking? I'm really not joking. Like I've spent a huge amount of time working on picking the appropriate emoji for these automatically. Yeah. But crucially, all of these things have happened, but only the things at the beginning had to work in order for my card to work in the store. And then if we'd had partial failures, all of these things would have kind of happened later. So we had them on a queue, they would have been processed later. We might not have sent the push notification if it was too far delayed, but all of our systems would pick those things up. However, in reality, it's actually a lot more complicated. This is actually what happened, which sounds insane. But crucially, again, we have this small section right at the top, and those are the only things in our entire system that have to be available in order for our cards to work. And that's the most important thing. Like, it doesn't really matter if we pick the right emoji, as long as every time I use my debit card, it actually works in the store. But by breaking our application apart into lots of small components, we can have like all these extra nice things which can break while still maintaining our like critical infrastructure, which processes card payments. The other cool thing we can do is we actually write log lines on every one of these requests. So we can aggregate all of these and we can actually like provide metadata on every single line. So even though we've like written a log line on, say we've passed through 20 different services, they're running on probably 20 different servers, which means in order to get the log lines for this request, I'd have to go to 20 different servers and look in those, or like search in something like the Elastic Stack and pick up all of these things. And you can actually search by request ID, so that actually works really well. And because we have this request ID, you can use commonly used tools to scoop up and aggregate all of these log lines into one kind of system of one kind of record of what happened. You can also put them in fun diagrams, but this isn't particularly useful. So this is actually a network of all of the services communicating to each other within our systems. And they get wider depending on how much traffic there is, and the color changes depending on how many errors there were. And they look really pretty, but they're not very good for debugging problems. So, hey-ho. What we found is Go is a really, really good language because it allows us to build quite simple infrastructure that is very easy to maintain. It's very, very performant. And fundamentally, the language itself is quite small and simple and easy to learn, which means we're able to bring developers on board and get them up to speed very, very quickly. The language itself has amazing features, so concurrency in particular. But there are, of course, a couple of downsides. So if anyone who's used Go, you'll notice there's problems with things like vendor management if you have lots of third-party libraries. This applies in any language, but if you have like Ruby, you have Ruby gems that solves this. Go does not have this, which means you have to kind of do this yourself. Thankfully, that's kind of been fixed a lot by the community. And the other thing is, being a young language, there won't necessarily exist libraries to do certain things. So in those cases, we might not choose Go, as Go might not be the right language for that particular problem. And then as far as starting with microservice architecture, in our case, we have started with a microservice architecture, which has pros and cons. We've ended up with a very flexible platform that we're able to work on very, very quickly. And as an example, last week, I needed to add a new service that added a new feature, and that took me about an hour to write, and I pushed it into our continuous integration system. All the tests passed. I pushed it into our staging system. All the kind of monitoring systems were fine, and I could push it into production. So I went from 0 to production in under 3 hours. And I could do that because I know that my service has it's not involved in any of the critical paths. So there were no changes to any other critical systems when I deployed my change. And giving like developers that kind of independence, I think will allow us to move much more quickly. And that's about it. Thank you very much.
So next is going to be a Q&A session. Please raise your hands if you have any questions, and there's one over there.
Yeah, one of the issues you usually face when you do microservice architecture, or anyway the old style architecture based on different applications, is the latency between the different services and between the different components. How did you solve that kind of problem?
So I think there's a number of things you can do there. As an example, okay. So the diagram I had up earlier, we had a synchronous section, and that is hitting, say, 4 or 5 different services, and we have a hard cap of about 100 milliseconds to reply, and that's really easy. As long as you're running on systems that are within the same physical data center, you should be able to achieve like a couple of milliseconds latency between machines. And as long as you are, if you have a language such as Go or Java or something that can maintain a connection pool, then you already have an established connection between these services. So in our case, we do direct connections. We have used a message bus in the past, in which case we used RabbitMQ. And actually when I worked at Halo, we had a service that did tens of thousands of requests a second, and the round trip latency was about 2.5 milliseconds. So that was 1 millisecond either way, and then it had like 200 microsecond processing time on the other side. So you'd think if for 200 microseconds, you could pull that into the binary, but the advantage of having these as completely different systems meant that this thing, like the things calling it, there were lots of different systems calling that system. And this one system we could scale because it had 20 or 40,000 requests a second, something like that. So my experience is you can get into service latency that's one millisecond or less, and I think like realistically that's good enough.
Over HTTP?
Yeah. If you have like an established connection, and things like Finagle, which is Twitter's library, they use either HTTP or MUX, which is kind of a lower level thing. But yeah, as long as you're not establishing a new connection and doing the negotiations and all those things, you can get the latency really low.
So on the right-hand side, we have a second question.
Hi, Matt. Firstly, thanks a lot. You set the stage perfectly for the Go workshop tomorrow that I'm conducting and for the Docker workshop. So thank you. My question is slightly related to what he just asked, but not regarding high latency, but with authentication. So as long as you're behind a firewall and all the services are together, no worries. I understand the millisecond rule. But if I need to authenticate services, does it actually bring down the total efficiency of the system?
Yes, and it gets quite complicated. So Kubernetes is a good example of a system that does do this. So if you provision a container onto Kubernetes infrastructure, it provides you with shared secrets that you can use to authenticate, and you can establish service accounts. So the main problem that we've seen is if we receive a request from the internet, from someone's phone, then they already have signed in, they have an authorization token. We do check that those are valid, which means that every request we have to hit an authorization database, we have to confirm that it's still valid, which is a problem. But then beyond that, we validate the token and we can pass that token down, which is signed and has scopes and expiry time. The main problem, and for 100 milliseconds request time, like that's fine within that period of time. The main problem I see is if you're doing things asynchronously, in which case that may go into a queue. The queue may last 12 hours, the token would expire. So you can't do those things later. And that means that your services that are doing asynchronous calls or services that initiate their own calls to other services will have to do some form of service authorization and have service counts.
Right, and the issue of debugging, when something goes wrong, the only way between microservice is to debug between which microservice has actually gone down and where the exact the problem is. The only way is to go through the entire log stash.
No, so we have a couple of internal monitoring systems. So firstly, every request that goes through every server within our infrastructure, we aggregate like a lot of metrics and we pass those off to an internal monitoring system. So if we go above like 1 or 2% errors, then we'll flag that as like a service failing. That usually implies that someone has deployed a service that's not compatible. In the other cases that we have system failures, we'll usually see things like our Cassandra health checks failing. Not necessarily on Cassandra, but the services themselves have these built in as well. So we have some idea of where the problem is. And then beyond that, we use a couple of tools. So every request has a request ID. We log all of those things actually into Logstash. So they go into Elasticsearch, and you can use Kibana to search on the request ID. So that gives you all the log lines for one request. But the real question is, how do you find a request ID for a server? Yeah. So we also use Sentry, which I think you can use as open source. I think you can download it and install it. They also provide it as a software as a service at getsentry.com. And our protocol between our services can encode an error stack that adds lines every time it bubbles up, and then sends those with an idempotency token to getsentry, where it aggregates all of this and gives us like nice errors. So basically, we can see that there's problems from our monitoring system. We can go to Sentry. We can see there's been 10,000 of this error. We can click on it. We'll get a request ID. We get some samples, and we can look at all the log lines. Yeah, it's a hard problem.
So we're gonna have one last question.
Fight to the death. I'll be here like all day and tomorrow, so.
Also, hopefully it should be a pretty quick question, but also I want to know, when you, I guess, have so many microservices, do you find that there's more of a management, a lot of management overhead in terms of kind of managing all of the deploys and managing all of the kind of services that connect each other? Because that's also related to the service discovery as well. So. Yep.
So we use, you could, for service discovery, if you were starting from scratch, I'd probably use something like Console, or in our case, we use etcd just as a consistent data store that we run within our cluster, and we've built a service discovery system. So every instance of every service heartbeats back to a centralized discovery service, which we run again multiple copies of, and that stores its data in etcd. The reason we need heartbeats is to ensure that we don't end up with a stale list of things in our list that no longer exist. So they expire after 30 or 60 seconds. And our services heartbeat every 5 or 10 seconds. We then integrate that with Linkerd or our client in our server, which looks at, if it wants to make a request to a service, it can go to this centralized service discovery, get a list, and then it can send a request on to that particular thing. So there is an overhead for sure. And you have to make sure that these things are entirely automated. Otherwise, there's like no way at all to monitor that. And as far as deployment goes, we have a very basic deployment system that allows you to specify a version of a service which gets the correct binary and then executes that as a Kubernetes deployment, which will run 6 copies of a particular service. And it has requirements, so it distributes them and doesn't run more than 1 copy on the same machine and things like that. But yeah, you have to build tools, and it has to be automated. Cool. Thank you very much.
Thank you, Mr. Heath.